So today we're going to start looking at trigonometry. Okay, it'll cover chapters 6, 7, and 8. One of the most basic things we need to know how to do is work with angles. Okay, there's two ways you can measure angles. I bet a lot of people have heard of degrees. There's also another unit besides degrees we'll talk a little bit about. All right, first thing I just want to make sure everybody understands is what is an angle. Okay, so basically an angle is when you take two rays, you have them start at a common point called a vertex, and they go off in one direction. Okay, that's an angle. Two rays, common vertex, and rays go off in one direction. Okay. Since we have two rays, okay, an angle has two sides to it. Okay. One side we call the initial side. The other side we call the terminal side. Okay, so let me try to show you a picture and keep this up. Okay, the way you can figure out which side is the initial and which side is the terminal is if you go in a counterclockwise direction, wherever you end up, that's the terminal side. Okay, so you always start at the side that's usually going to be horizontal, and the side you head towards counterclockwise, that's the terminal side. Okay, and as long as we're measuring things in a counterclockwise direction, we're going to be dealing with positive angles. Okay, we can measure things in a different direction, in a clockwise direction, but instead of dealing with positive angles, then we'd be dealing with negative angles. So really, when you draw an angle, there are two different angles you can look at. You can look at the one that's between the two rays, okay, where I have the red arrow, okay, or you can look at the one that's outside the two rays. Generally, we don't look at the one that's outside. We're going to focus on the one that's inside. In other words, the angle that's less than 180. Okay, so any question on the definition of an angle or the names of the two sides? Okay. When we name angles in trigonometry, a lot of times they use Greek letters. Just like in algebra, we use X and Y a lot, especially with coordinates. A lot of times we just use Greek letters for angles. Does anybody know the names of any of those angles? I think they know. How about the first letter in the Greek alphabet? Alpha. Beta. Delta. There's no delta up here, but you can use it. Yep, gamma's up there. That's theta. Can we get them all?
Epsilon.
No?
Foxtrot.
That one's omega. Okay, these are all lowercase. You might have seen capital omega. Okay, that one looks like a horseshoe kind of. They use that for resistance in electricity. Okay, but that's a capital letter. We're not going to use all of these today, but throughout trig, we'll see all of these at some point. Okay, so generally, when we want to represent an angle, we pick one of these letters. Okay, and you'll see why we use different ones in different cases. Okay, does everybody have what's on the left? Okay. All right, so okay, so when we draw an angle, we like to draw it in a way so that we're consistent. Okay, because technically you could draw an angle and you could just take and turn it any way you want. But generally, if we're asked to sketch something, we'll do it in what's called standard position. Okay, to sketch an angle in standard position, two things have to happen. Okay, the vertex has to be at the origin. Okay, so you need a set of axes. And you put your initial side on the positive x-axis. Okay, if you've done those two things, then you have an angle in standard position. is that angle in standard position?
Yes.
No.
No, what's wrong with it?
No.
Yeah, the initial side is still on the positive x-axis, but the vertex is no longer at the origin. Okay, what if I did something like that? Is that standard position?
Yeah.
No. What's wrong now?
Not on the x-axis.
Right, now the initial side is up in the air. It's not on the x-axis. The vertex is at the origin, but you got to have both. Okay? That's standard position. Okay. Any question on what standard position is? Yep. Right, so one way that we can measure an angle is in degrees. We can also talk about like a rotation in terms of, we could also translate that to degrees, but a lot of times we'll just use degrees. But one thing that's going to help us out is if we know how many degrees in a rotation. Okay, so how many degrees make up a full rotation? 360. Okay, so 360 degrees is one counterclockwise rotation. What do you think would happen if I said negative 360?
Goes counterclockwise.
Negative 360?
Clockwise.
Yeah, negative 360 would be a clockwise rotation. All right, so we have to get used to this idea that positive angles are measured counterclockwise. Counterclockwise is this way. Okay, so what about a half counterclockwise revolution? That would be 180. And what about a quarter revolution counterclockwise? 90. And again, we're doing all this in degrees. Okay, so angles that are measured counterclockwise are positive. If we measure an angle clockwise, that's negative. Right, not only can we measure a full revolution, but we can go beyond a revolution. What do you think happens to the number when you go beyond one revolution? It gets bigger than what? Yeah, we can have angles that are bigger than 360 if they make more than one revolution. And we can have that in the clockwise and the counterclockwise direction. So either bigger than 360 or less than negative 360. Okay, here's an example of a program that just lets me draw angles always in standard position. Okay, initial side I can't move, the terminal side I can, and it tells me what the angle measures in degrees and another unit which we'll talk about. Okay, so as I start to go around, there's my half revolution, okay, 3/4 of the way around, and finally one full revolution.
Why does it say on the bottom like the TT?
This one? Yep, 2 pi. We'll talk about that. Okay, as I go beyond a revolution, my angle goes beyond 360 degrees. Right? So we can see that where I stopped for 630 degrees is exactly the same as where I'd stop for 990, which is the same as where I'd stop for 1350. All these angles have the same stopping point for the terminal side. In this case, straight down on the y-axis. So what we usually like to do if we have an angle that's too big, 1350, is we make it smaller. We take away 360 degrees or a revolution. And we keep doing that till we finally find the same terminal side, but the angle is much smaller and easy to work with. Okay, same idea if we go negatives. Okay, negative 90 is exactly the same as all those other angles I just said. Now we're going in a clockwise direction. Okay, we'd usually put a little arrow on here so we could see which way we went. And same idea if you do more than one revolution, it gets more and more negative. Okay, so any question on that? Okay, and there's a name for angles that have the same initial and terminal side. Okay, like this one. Let's go this way. This one. And this one. Okay, if you were to block what was on the board here and not look at the red spiral, you wouldn't be able to tell the difference between any of the three angles I just drew. The initial side was on the x-axis, terminal side, negative part of the y-axis. Okay. If you have angles where the initial and terminal side are the same, those are called coterminal angles. Okay. A very easy way to find coterminal angles, all you have to do is take what you're given and add 360 degrees or subtract 360 degrees. You could do it as many times as you want. Okay, so what we'll try doing is we'll sketch an angle in standard position. They'll give us an angle. And then we'll find two angles that are coterminal with it. We'll find a negative one, and we'll find a positive one. Right. And to do that, just keep in mind the trick for finding coterminal angles. Right, so let's start with 30 degrees. Okay, we're not going to use a protractor. It doesn't have to be perfect, but it should be a reasonably good sketch. Okay, what kind of angle is a 30-degree angle? It's a Q. All right, so we definitely know it's less than 90, so it's going to be contained in the first quadrant. Should I draw my terminal side halfway? No, that'd be a 45. I want to go a little less than halfway. Right, so a 30-degree angle might look something like, let's go like this, like that, and maybe about like that. Okay, what I'll do is I'll make them a different color so you can see my angle. Okay, so there's a 30-degree angle, and I want to find two coterminal angles. All right, so let's start with positive, and then we'll do a negative. Okay, how would I get an angle that's coterminal with 30 and positive? Yep.
Add 4 minus 360 degrees from, oh, no. Wait, yeah, for the 30 degrees.
So what did you say? Just add?
Add or minus the 360 degrees with rotation.
Yep. So in this case, I want a positive one, so would you add or subtract?
Add.
Add, and what's 360 plus 30?
390.
390. So 390 and 30 are coterminal. Okay, how about negative? What would be 30 minus 360?
Negative 330.
Negative 330. Okay. Any questions on that? Okay, 145. What kind of angle is that? Yeah, it's obtuse, so it's more than 90, so it's going to be into quadrant 2. Okay, so this is 0, 90, 180. Is it my terminal side closer to 90, closer to 180, or right in the middle? So you think 145 is...
No, it's close to the one.
Yeah, 145 is a little closer to 180. 135 is right in the middle. Okay, so 145, just make it a little closer to 180. So always put your initial side there. Okay, that's about halfway. Just make it a little more. Okay, and there's my angle. And same thing to find two angles that are coterminal. Okay, start with a positive. So I'll take 145 and add 360. So we get 505. And for my negative, take 145 and minus 360. Negative 215. Okay, given the choice of the three ways to represent this angle that we have on the board, 145 is probably the best. You don't have to think about numbers that are too big, and you don't have to think about negatives. Okay. Okay, and negative 45. All right, so let me sketch my initial. Okay, well, where's my terminal side going to be? Down which quadrant? Yeah, that's going to be in quadrant 4. Is it going to be closer to 0? Is it going to be, let's see, this would be negative 90, which is the same as 270? Or is it going to be right in the middle? Yeah, it's right in the middle. Okay, so that's a negative 45. And lastly, find our two angles that are coterminal. Okay, what would be an angle that's coterminal and positive? How much? Kyle?
400.
No, not 400. 315. Yeah. Okay, because if you take in negative 45 and add 360, it's like 360 minus 45. Okay, so 315. Now for the negative one, it is going to be negative 400 something. What's that one going to be? Negative 405. Just take negative 45 minus 360. Okay, so questions on sketching angles or finding coterminal angles? All right. Okay, so let's go over some quick basic definitions. Okay, what does it mean for an angle to be acute?
Less than 90.
Okay, less than 90, that's part of it. And there is something else. It has to be greater than 0. Okay, so theta here, it's one of our Greek letters. Theta represents an angle. So for example, negative 10 is not acute. Okay, it's got to be greater than 0, less than 90. Okay, how about a right angle?
More than 90.
No, not more than 90. That's going to come up in a little bit. But a right angle is exactly 90. Okay, bless you. Okay, how about an obtuse angle? Greater than 180, there is actually a name for that. I'm not going to put that one on the board, but I can mention it. Greater than 90?
Less than 180.
No, not less than 360. We got to be more restrictive than that.
180.
Less than 180. Okay, obtuse angles cannot be more than 180. They have to be greater than 90. An angle that's greater than 180, does anybody know the name of that? It's not one I'm going to do, but that's a reflex angle. Okay, if you have an angle greater than 180, that's a reflex angle. All right, how about complementary angles? Cheryl? They add up to 90?
Yeah, like the different degrees.
Okay, that's part of it. But there's something else here.
Like the same.
They don't have to be the same. You could. You could have like a 45 and a 45. That's a special case
They
of
have to share
like a side or?
Yeah.
That's adjacent angles. So if we're thinking back to geometry, two angles that are adjacent share a side. You can have two complementary angles. We can have one in this room, one in the next room. That's fine. As long as they add up to 90, and if I give you an example of what's not, you'll know what I mean.
Do they have to have like a bisector to be agreeable?
Nope. In a bisector.
Not a bisector, but like, I'm not sure what they're for.
Think back to acute angles. Acute angles had to be less than 90, but what else? greater than 0. Okay, so here it's the same idea. The angles have to be positive. Negative 10 and 100 degrees are not complementary. Okay, so you have to have two, I guess you could say two acute angles that add up to 90. And what about supplementary?
Add up to 180.
That's part of it, add up to 180.
Greater than 0.
And they have to be positive, yep. So negative angles do not have complements or supplements. Okay, so what we'll do, we'll just take some angles and we'll try finding the complements and supplements. Okay, what do you basically do if you have an angle and you want its complement?
90 minus 40, whatever it is.
Yeah, 90 minus whatever your angle is. Okay, so what's my complement to 48 degrees? 42. Okay, and what would be the supplement?
132.
132. All right, how about, let's try negative 18. Nope, no complement. How about the supplement? No supplement. All right, how about x degrees?
It should be x for like another letter. Because you don't know x, so you can't do it.
Yeah, 90 minus x. That's the complement. Okay. Here we have to assume that x is an acute angle. If x was 100 degrees, it doesn't have a complement. All right, so assume x is acute. Okay. Now for the supplement, we don't have to assume that. X could be 100 degrees and we could still have a supplement to it. Okay, but we'd have to assume x is at least less than 180 in that case. All right, so what would be my supplement?
80 minus x.
Yep, 180 minus x. Any questions on complements or supplements? All right. And last thing, okay, probably the most important thing for the trigonometry part today. Okay, so when I had that diagram on the board, there were two numbers, okay, showing you how big the angle was. Okay, so you had this 270 degrees, and then we had this 3 pi over 2 number. Well, that 3 pi over 2 is another way to measure an angle, and that's called radians. Has anybody ever heard of radians before? Some people work with them a little bit. Okay, does anybody see, almost not exactly, but a word having to do with circles that almost kind of hidden in the word radians? Almost radius, yeah. Okay, if you just look at it, we have most of the letters there except the U in radius. So radius and radians, there's a connection between them. Okay, I'm going to show you the connection with this diagram. Okay, so what I've drawn here is a central angle. It's just an angle in the center of a circle. Okay. One of the sides of the angle is ray CB. The other one is ray CA. Well, CB comes out from the center and it hits the circumference right there. CA comes out from the center and it hits the circumference right there. If I connect those two dots I just drew, that portion of the circle is called an arc. Okay, and the notation for that is arc AB. And I'm going to use this diagram to show you exactly the connection between a radian and a radius. All right, so now let's suppose we took a piece of string, okay, and we measured the length of that arc. Okay, so we laid the string out, we measured the length of it. And then we took and measured the length of the initial and the terminal side. Okay? If the length of this arc measured exactly the same as the radius, then this angle would be 1 radian. Okay, so it's a special relationship. So angle ACB would be 1 radian if the length of this arc and the radius are exactly the same. Okay, in this diagram, I don't think they would be. To me, it looks like the arc is a little bit longer than the radius. Okay, but if they came out exactly the same, then this angle would be 1 radian. Okay, this idea is very important. If the length of the arc equals the length of the radius, your angle is 1 radian. We're going to come back to that maybe tomorrow or at some point during the week. All right, so visually, that's what a radian would be. Arc length matches radius length. We know that this is 1 radian. But what we really want to figure out is how we change between what we're more familiar with, degrees, and probably what we're less familiar with, which is radians. Right, so this will be the last thing we look at, how we change between degrees and radians. Okay, we're going to try to figure out what the conversion is. Okay, and I guarantee you already know the pieces you need to find the conversion. Okay, with an idea from geometry and me helping you out, you'll be able to hopefully figure this out. Okay, so what I have on the board here, this is a circle, and it's a circle with a radius of 1. Okay. As long as you have a radius of 1, okay, the name of that is called a unit circle. Okay, unit circle is just a circle with radius 1. Okay, and our goal, what we need to figure out is a connection between the size of an arc and the size of an angle. Okay, we need a connection between those two things. Okay, kind of like if I said to you, I want you to come up with a formula for converting feet to inches. You've got to have a starting fact. Okay? Here's a good starting fact that would help you convert feet to inches. 1 foot is 12 inches. Using this fact, you could figure out, you could convert any number of feet to inches or any number of inches to feet. You could just set up a proportion. 1 foot is 12 inches. In 4 feet is how many inches? But the key is you've got to have this starting fact. Okay? You've got to have something you already know that's true to find out things you don't know. Right? So we're going to try to do the same thing here. We're not going to come up with something between feet and inches. We're going to try to come up with a connection between size of arc and size of angle, okay, in radians. And once we can get that connection between two things, we can use it to figure out other things we don't know. Right, so in a unit circle, something special happens that's going to make finding this connection a little easier. Okay, and this is only in a unit circle. In a unit circle, the measure of the angle is the same as the size of the arc. Okay? In a unit circle, the size of the angle, as long as you're measuring in radians, okay, not degrees. Okay, so in a unit circle, the size of the angle is the same as the size of the arc. They're the same thing. And because of that very special property, that's going to make finding a connection between size of angle and size of arc very easy. They're the same. Right, so basically all we have to do is try to find an angle that we already know the length of the arc for. Just like we have a measurement here, we already know the number of inches for it. We've got to have something we already know, and you guys do. Okay, so this last part after so, this is just what, you don't have to write that, but that's what we're going to do. So we've got to think of an angle in our head that we already know the length of the arc for it. Okay, let me give you a hint. I want you to think of an arc that's so big, it's not just part of a circle, but it actually takes up the entire circle. Okay, what do we call an arc in geometry that goes around the entire circle? It's the circumference. Okay, the circumference. Now, do we have a formula to find the length of the circumference? We do. Okay, it's not just an arc, it is an arc, but it's an arc that's so big we call it the circumference. Circumference is 2 pi times r. Now, we know that a circumference is the same as one full what? Circle or revolution. So, my point here is if we can find the length of this circumference, the length of this arc, it's going to be exactly the same as the length of an angle that goes all the way around the circle in radians. Okay, so all we have to do is find the length of the arc, and it's going to be equal to the angle in radians that goes all the way around the circle, because the circumference goes all the way around the circle. All right, so let's see if we can find the length of the arc, and that's going to be equal to the length of the angle. Okay, on a unit circle, what's my radius? 1. What's 2 pi times 1? 2 pi. That's the length of the arc that goes all the way around the circle, 2 pi. And if that number is equal to the angle that goes all the way around the circle, what's the angle in radians that would go all the way around the circle? 2 pi. They're exactly equal. Okay? And we could see that on this diagram. Okay? If you go all the way around a circle, it's 360 degrees or 2 pi radians. Okay? So that's where the 2 pi comes from. All right. So now we know 1 revolution is 2 pi radians, which is the same as 360 degrees. Right, now, this conversion is fine, but generally we like to get our numbers a little smaller. What could I divide each side by to make things smaller here? 2. So instead of saying 2 pi radians is 360 degrees, I could say pi radians is 180 degrees. It's the same thing. It's like if I said to you in 3 feet there's 36 inches. Well, why don't we simplify it and just say in 1 foot there's 12 inches. Just a simpler way to say the conversion. Okay, but anytime you give someone a conversion, it usually has a certain number in it. In 1 minute, 60 seconds. In 1 day, 24 hours. Okay, in 1 hour, 60 minutes. In 1 mile, 5,280 feet. Every conversion I just wrote up here has what number in it? 1. Usually when you give someone a conversion, it's easiest if you tell them it with a 1. Instead of saying, oh, in 3 minutes there's 180 seconds. That's true, but this is simpler. Okay, what could I do on each side here to say, let's get a 1 on one side of this equation?
You have to divide by 180, right?
That's one way I could do it. So I could take pi radians equals 180 degrees and divide both sides by 180. 180 divided by 180 is 1. So now this tells me 1 degree is pi over 180 radians. Okay, so now I know exactly how much 1 degree is. What could I multiply both sides by if I wanted to know 2 degrees?
180.
Yeah, if I multiply by 2 and by 2, now I've got an equation that says 2 degrees is that many radians. Okay, if I wanted to know 8 degrees, multiply by 8, multiply by 8. Now 8 degrees equals this. I just have to do it out in radians. So the key is, if you're trying to change from degrees to radians, you multiply by pi and you divide by 180. Okay, so to change from degrees to radians, these are the 2 steps. Multiply by pi, divide by 180. Okay, and now to change the other way, we reverse that. Okay, it's similar, but it's kind of in reverse. To change radians to degrees, you multiply by 180 and you divide by pi. Okay, and as we do a problem, I'll give you an easy way to remember that. Okay, but one thing you have to remember is when you think degrees, the number I want you to think when I say degrees, whoops, put that back. So I get it up. When I say degrees, I want you to think the number 180. When I say radians, okay, I want you to think pi. So I want you to connect those 2 things. Pi, think radians. Think 180, think degrees. Okay? And that'll avoid having to memorize this. Let's look at an example. We're going to change 30 degrees to radians. So our 2 choices, we're either going to multiply by pi over 180, or we're going to flip it and make it 180 over pi. Okay. The way that I try to remember, if you want to think of 30 as a fraction, you could put it over 1. Where's degrees in this fraction on the left? It's in the top. I want it to cancel out. I'm trying to get radians. So where would it have to go to cancel it out in the top of the other fraction? Degrees would go in the bottom. Radians would go in the top. So now degrees and degrees would cancel. Now, what number did I say to always think of when you think degrees?
180.
180. What number did I say to always think of with radians? Pi. And now we just multiply it out. 30 pi over 180. Okay, generally we don't write it as a decimal. Just reduce it as much as you can. 30 goes into itself once. How many times does 30 go into 180? 6. And the answer is pi over 6. Okay, one thing you do have to get used to is you're not going to see RAD written. If you see an angle written and there's no label, you assume radians. If they want degrees, they have to put the little circle. Right, let's try one more of these, and then we'll try one in the other way. Okay, where would degrees go to cancel out? What number do you think of with degrees? 180. What number do you think of with radians? Okay, pretend RAD is written. I want you to get used to not seeing it. And 60 goes into 180 how many times? Yep. Leave your answer as pi over 3. Now, if the angle is not a multiple of like 30 or 45, like if say it was 36 degrees, they'd probably have you type this in and round it. Right, so let's just finish up. We'll change this one to degrees. All right, so if you need it this time, I'll write RAD. Okay, RAD is in the top. Where would it have to go to cancel out? Means degrees is in the top. Number with degrees? Number with radians? And now watch what cancels out. Radians cancels, but what else cancels? Pi. And now I'm left with 2 goes into 180, 90 times. What's 3 times 90? 270 degrees. Okay, I do need to put the circle on it if I'm changing to degrees. Okay. So that's the basic idea, changing between degrees and radians. Okay, we can practice more of those tomorrow if we need to. Okay. If they ask you to round, just type it into your calculator. Literally, type in 500 times pi, divide by 180. But use pi button. Don't use 3.14, it's not accurate enough. Okay? And same thing, converting the other way. All right, so we can practice more where we round tomorrow. All right, so that's the homework for tonight. If you don't get it, it will be online. But it's basically very quick little problems. Complementary, supplementary angles. Change to degrees, change to radians. Shouldn't take too long. Okay, so we'll take a look at that first thing tomorrow. Okay, so homework tonight is page 323, numbers 1 to 3, 7, 9, 11, 12, 15, 24 to 26, 30, 35 through 37, 41 to 43, 47, and 51 through 53.